additive manufacturing. Sandeep, can you open it? There is some problem with this presenter. Yeah, next. So this is the brief outline of the presentation. I will be taking you through the traditional manufacturing processes, highlighting some of the drawbacks or limitations, so that you will be able to appreciate the importance of the additive manufacturing technologies, right? Yeah. And also I'll present some of the exciting applications of 3D printing, and finally we will see some barriers or challenges associated with the 3D printing process. Yeah. So this picture, when you look at, so we have a saying that a picture is worth 1,000 words, right? So this boy lost the fingers, okay, and you know how difficult it is for the for a boy at that age particularly to cope up with physical challenge, especially among the peers, all that. When the guy is not able to perform the routine activities, you can understand the kind of pain the kid will undergo, right? So, and you can see the solution provided through the 3D printing or additive manufacturing. Okay, the artificial fingers have been made, okay, and attached, and he can handle the things easily now. Okay, of course it is not 100% like natural fingers, but to a great extent he can overcome the difficulty. Okay, so yeah, we all know the kind of impact the internet has created in our lives, especially from the late 90s. Okay, the internet has penetrated into all spheres of our life in various sectors. So you can't name a sector where internet is not used, isn't it? Such an impact it has created. And interestingly, some of the sources, including Financial Times, says that 3D printing is potentially larger than internet, right? So that is the importance of 3D printing or additive manufacturing. Okay, so I don't have to elaborate or convince you to make you understand that how important the additive manufacturing is in the days to come, especially now it is in the emerging stage, but it is going to have a lot of impact on all of us in various ways. Yeah. So the traditional manufacturing processes, yeah, we all know the how parts or components or products are manufactured using casting process, right? So you make the mold, you melt the metal or plastic, whatever, okay, pour it, and it assumes the shape of the cavity, and when it's solidified, you get the component. Once the after the solidification, of course you will have to remove these kind of things, okay, the unnecessary things, screws, runners, gates, all those things you have to remove. So that will be possibly recycled, okay, for the next component. All right, and this is the main component. And you see, for realizing this component, there is a process change here, right? So it all starts with pattern making, right? You need to apply the tolerances for the pattern, different allowances you have to apply for the molding process. Okay, metal may shrink, so accordingly you have to apply these solidification, shrinkage allowance, and many other things, machining allowance, all those things, right? And then you have to melt the metal, prepare the mold, and then pour it, allow it to solidify, and then remove the unnecessary elements involved there, screws, runners, all those things, and then it has to be taken for heat treatment, okay, after solidification, maybe further machining, finishing, okay. This is the process chain, entire process chain in the case of conventional manufacturing processes, okay. So it involves elaborate process chain. That is what I wanted to stress here. Yeah, next. So here is another process, powder metallurgy or particulate processing. Again, you need to make the powders, right? And then, introduce the powder in the, pre-designed, what you call the molds, compress the powders, okay? And immediately after compressing, you will not be able to get enough strength on the part because it is only a green component, okay? It is not suitable for readily deploying in the, applications, right? So you have to again heat it in order to give enough strength for the component, all right? And then of course some machining or finishing, whatever required, you will have to, make the component to undergo through that process, all right? So here, for you to get a particular shape of a component, you need corresponding, molds or dies, isn't it? The moment the part shape changes, your die also has to be changed, isn't it? Same die cannot be used for manufacturing any component. That's not possible. That is the limitation. Okay. Next. So this is forging or deformation processes. Again, part specific dies are required. Right. The moment the shape of the component changes, correspondingly die shape has to change. Next. In the case of material removal processes, machining processes, can we use same tool for carrying out different types of machining operations?
No,
Possible?
No, sir.
It's not possible. You have to use maybe one particular tool for thread cutting, another tool for facing operation, one tool for turning operation, right? Knurling. So different tools are there. Depending upon the operation, you need to use corresponding tool, right? So again, part specific tooling is required in this, process. Yeah. So to summarize the limitations of the conventional processes, what are the drawbacks or limitations? Material wastage. What are the other things? You can easily enumerate.
Multiple number of components.
Multiple number of.
Components.
Yeah. So to realize one component, you need so many different types of tools or molds. Okay.
Design complexity.
Design complexity, very good. So you can't achieve any complexity, whatever you think of in the mind. It is very difficult, at least we can say. Okay, we don't say impossible, but very, very difficult to realize such a complexity, whatever you think in the mind, okay, to realize as a physical component through the conventional manufacturing processes. Okay.
Everything setup is to be changed.
Yeah, you need to go for a different setup as the component changes. Okay, that is why you set it up, you set up the machine for one particular component, produce certain number of components, and then switch over to next component. Okay, we call it batch production, or in the case of mass production also. Okay, so you have to produce enough number of components. So you have to stick to particular setup. So each time you can't undertake different component. The moment you undertake a different component, setup has to be changed. Tools are to be, they are different, and program has to be different. Okay. So all these things are, the limitations or drawbacks. Yeah. So part specific tooling, last minute changes. Okay. Everything is set up, and finally you wanted some change in the design. Okay. That is very difficult to accommodate. Then you have to go through the entire, process, chain in the manufacturing, right? Yeah. Number of process steps and resources. You have a long process chain in the case of conventional manufacturing processes. Reverse engineering is difficult. So what is reverse engineering? Some of you may be aware.
We can take a dimension from an old part, or we are using common to.
So is it legal?
So that is not illegal, but
But like the old archaeologist type and those things, you can get back to the shape.
Yeah. So it is legal under certain conditions. If it is not legal, we would not be discussing about that. Right? So it is legal only under certain conditions, right? What are the conditions? For example, documentation is lost for some component because of some reason, okay? Then component is available, but documents are not available, okay? So from this component you can generate all that documentation, by scanning the component using the the 3D scanner, things like that, and you can develop the drawings, all those things, and then again start manufacturing, okay? You have some component, your opponent is manufacturing, you are in an industry, okay? The competitor is manufacturing the similar component, okay? You can buy that, study that, okay, by reverse engineering techniques, and then improvise upon that. Nobody is going to stop when you say I am going to improve that, okay? That is required actually. If you produce as it is and then dump it to the market, that is not correct, that is not ethical also, okay? You study the component, understand what are the drawbacks of that particular component or product, improvise upon that, and then you can release it altogether different version. That is always encouraged, in fact. Yeah. So you have this reverse engineering is very difficult. I don't say impossible in the case of conventional manufacturing processes, but very difficult.
Manufacturing was stopped a long time back.
Huh?
And then manufacturing of the component was
Stopped, yeah, long time back, but suddenly one customer has come forward for that particular component. Yeah, and you don't have any traces of that component, no drawings, nothing is available. Then you can still manufacture using the reverse engineering concept. Yeah. On-demand manufacturing is very difficult. Okay, somewhere you are in the forest, let us say, some component is required there. Okay, if you can't carry big lathes or milling machines there, right? It is very difficult. So that is the limitation again. Repair work is difficult. A component is there, let us say a turbine blade is there, which is a very complex, free-form surface actually. It is not a regular surface, turbine blade. And somewhere some damage has occurred to the turbine blade, right? So instead of replacing the entire turbine blade, which may be costly in terms of the material cost, in terms of the manufacturing cost, all that, right? You would like to repair that particular region and then still use that. That is very difficult using the conventional manufacturing techniques. Repairing some local region and then again using the component. Okay, yeah. So what if you have you require just electricity, okay, access to some raw materials and a computer. With that, if you are able to manufacture something, right, so that will be wonderful. Next, for example, your watch, there is in the buckle some repair, okay, so immediately we think of replacing the entire thing with a new band, right? Instead of that, at your home itself, if you have such a facility, you can just manufacture that small component and then attach it, replace with this one, okay, and then use it, okay. That is the convenience you get. And we know the hearing aids, different geometry may not be altogether different, but slight changes. See, your ear geometry is different from that of your neighbor, okay. So same hearing aid may not sit properly in your ear, ear, okay. Different people will have different geometries, all right. So mass customization we call it. Mass production we all know. Same component with same dimensions, geometry as it is, producing it in thousands, lakhs. That is called the mass production, right? Mass customization is a new concept. Mass customization means you produce that particular item with slight variations in the sizes, in the geometry, okay. Still you call it hearing aid, but they are all different in terms of sizes, in terms of the geometry, okay? And you want them to be produced in hundreds, thousands, lakhs with those variations, right? So that is called the mass customization. So that is very much possible in the case of additive manufacturing process. Next. So the, let us say, Word document, that is a digital item or information, okay? So you have the digital thing, and you have printer, 2D printer, okay, the document printer, okay. So you are converting digital to physical. In the similar fashion, next, 3D printing is also converting digital information into physical component. Instead of a paper, instead of a document, okay, we are converting digital information into this, the physical component, three-dimensional component. Suppose you want to manufacture this sphere, okay. So what is the old way? The block of, you take a block of material, you carve it, okay, realize a sphere, okay. That is going to take a lot of time. The modern way is that you generate a 3D model, solid model you can generate using any of the softwares like, the CATIA, the SolidWorks, okay, Creo, things like that. You can generate the solid model. And then you generate the CNC program, okay, and you load this CNC program into the machine, CNC machine. So the machine will be, removing the unwanted material and then produce the sphere finally, okay. So the unwanted material which is obtained, you may have to recycle it, okay, melting and again use it for producing the different components, okay. This is a process chain in the case of CNC machines. Next, in the case of 3D printing, the steps go like this. You generate a 3D model, okay, like in the case of in the previous case, and then your software will be slicing the 3D model, virtual model, into different layers, okay. It will be slicing virtually, and then 3D printer builds the component layer upon layer. That is how you realize the entire physical component. All right, that is how the 3D printing goes. Next. So how do you define 3D printing? It is a process of joining materials to make objects from 3D model data, usually layer upon layer, all right, as opposed to subtractive manufacturing technologies. This was the definition given by ASTM in 2010, and later in 2015 this definition was withdrawn, saying that this definition will not capture the entire philosophy of the additive manufacturing. This definition is not complete, okay, and even now there is no complete definition for additive manufacturing, okay. So that is the that is the stage in which additive manufacturing is today, okay, which means it has got lot of potential, okay. It is not matured yet, okay. So it has lot of potential, and you have lot of scope for research in additive manufacturing. So the key attributes of additive manufacturing: physical form from digital. You get the physical from the digital. No part specific tooling is required, okay. Same machine you can use for producing altogether different products, right. And progressively adding the material layer by layer, all right. So in this 3D printing or additive manufacturing, you have different names: rapid prototyping, which was used in the early stages, rapid prototype, because this technology was used for mainly producing the prototypes initially. But nowadays you can see additive manufacturing being used in the industry for end user products also, direct, okay, not just prototyping alone. Also you call it rapid manufacturing, additive manufacturing, solid free form fabrication, direct digital manufacturing, and there are many more names for this. Yeah. Can you click that? I will just show you some video. Always talking will be boring.
Fused deposition modeling, or FDM, is a layer additive manufacturing process that uses production-grade thermoplastic materials to produce both prototype and end-use parts. This technology is known to accurately produce feature details and has an excellent strength-to-weight ratio. FDM is ideal for concept models, functional prototypes, manufacturing aids, and low-volume end-use parts. The FDM process begins by slicing 3D CAD data into layers. The data is then transferred to a machine, which constructs the part layer by layer on a build platform. Thin thread-like spools of thermoplastic and support material are used to create each cross-section.
So
of
you
the
can
part.
observe there are two types of material. One is build material, another is support material.
Similar to a hot melt glue gun, uncoiled material is slowly.
So you have two nozzles, one for build material, another for support material.
Precisely lay down both support and thermoplastic material on the preceding layers.
So this white is the support material, black is the build material, with which actual component is manufactured.
The nozzle continues to move in a horizontal XY plane while the build platform moves down, building the part layer by layer. The finished part is removed from the build platform and cleaned of its support material. Raw FDM parts have visible layer lines. However, service providers such as Solid
So you can see here the white material, which is support material, being removed in the post-processing stage.
Assembly, and cosmetic paint. Since FDM parts are constructed with production-grade thermoplastics, including ABS, polycarbonate, and ultim, they are both functional and durable. FDM is utilized in a number of industries, including aerospace, automotive, industrial, commercial, and medical.
So the word that used FDM is one of the additive manufacturing technologies, fused deposition modeling. FDM stands for fused deposition modeling. Like that, you have several different techniques available. Okay, so yeah, you can observe here the various sectors, relative percentages of additive manufacturing components being used there. Okay. So motor vehicles, aerospace, industrial business machines, consumer products, okay. So this is the spectrum of the additive manufacturing. Next. So whenever a new technology is introduced, it undergoes this particular cycle. We call it hype cycle. Okay. In the year 2013, the additive manufacturing or 3D printing, you can see somewhere at the peak of this cycle. Okay, so it is very calm. You see, you might have observed, some time back, everybody was talking about nanotechnology, right? So as if nanotechnology is going to rule, everywhere, everything. Okay, without nanotechnology, nothing will happen, or all those things will be spoken. And recently also we are hearing data science, machine learning, okay, so artificial intelligence. So these technologies will be undergoing this particular cycle, hype cycle, okay. So initially they will be starting slowly and then assume the peak, okay. That is where the word will become buzzword everywhere. People will be talking so much about that particular technology, and then later in course of time, people won't be talking about that much, because there will be so many difficulties. People will be realizing, okay, and it attains this particular trough of disillusionment, okay. People will be in that phase. People will be thinking this technology is of not much use. It is not practically viable. It is not going to help us. All these things, okay. But people will be working on the drawbacks or limitations of the technology, and then slowly it will be gaining the popularity or importance. This is how the technology undergoes the cycle. Okay, so the in 2013, we, as you can see here, the 3D printing was at the top, okay, in terms of the popularity, all that. And now we have seen all these things, and it is slowly maturing. We can say that the technology is maturing because many people are working on this technology to overcome various difficulties or limitations. Yeah. So the current status, AM technologies are rapidly evolving. Okay, better and cheaper machines. There is healthy competition. See, in the year 2009, the patent, especially Stratasys company, which patented the technology FDM. That expired. Okay, in the year 2009. The moment a patent expires, people in the market will be will start producing the machines because no more patenting binding is there on the. So different companies will be parallelly, simultaneously will be developing the machines, and that is how you can see the growth. Otherwise, earlier it was only monopoly. Okay, so whatever Stratasys builds, whatever price they quote, you have to buy that. Not only buying the machine. As you might have observed, when you buy a printer, normal document printer, initial investment you will have to bear. That particular company will also try to have the secondary business. Like you need to buy cartridges from them only, right? That is the secondary business for the company. Okay. So similarly, these 3D printing companies, 3D printer manufacturing companies. When they sold out the machines, they were insisting that, you have to buy material from us that is authentic. If you buy another material which may be available with the different vendors, if you buy that, your warranty will be lost. You don't risk when they say, when these conditions are there in the purchase order, all that, isn't it? So you try to buy the materials from them only, and they will be naturally selling those materials at a higher rate. That is their business. Okay. So the moment these patents are expired, you have the free market. Anybody can manufacture. Nowadays, even before we ask, recently we wanted to buy a machine, metal 3D printer. We invited the prospective vendors. Okay. So they came and they presented, saying that even before we asking about the material, they themselves said, you don't have to buy material from us. To motivate, to attract us to buy their machine. Okay. Earlier, that was a limitation. Okay. So that is the advantage you get when the patents expire. So nowadays you are getting the better machines, cheaper machines, because there is a healthy competition in the market. Advances in online monitoring and also process control. Okay, so those things also will be incorporated in the newer machines. Whenever there is some development in the process control, all that, okay, online monitoring, all that, all those things will be incorporated in the newer machines. So you will get better machines, obviously, and bigger machines also nowadays, because you can't say I will only be manufacturing the components of this much size. Okay, you have the engineering components, very big, as big as aeroplane wing.